Hello again, my name is Antimatter and I'd like to talk to you about time. This is the third in a series of short talks which explores a theory where there are two dimensions of time and how that can explain quite simply some of the things that we see around us. And in this third talk I'd like to cover the question of why is there no antimatter around us, right? Everything in our world, everything we see is matter, but why is there no antimatter? In physics, everything we do is appears symmetrical. So if you create matter and antimatter from energy, you get a symmetry occurring in matter and antimatter, and yet around us there is no antimatter apart from when we produce tiny amounts in experiments. And why is this? Well, it is really quite simple to explain if you assume there is a Big Bang. Now, I'd like you to just go back to our explanation of the two dimensions of time, where we have a dimension of space and we ignored two of the other dimensions, so we can envisage the fourth dimension of time in this direction. And we envisaged, using our wrapping paper, every particle and everything in the universe travelling at a constant speed of light in that four dimensions. So it's either stationary in space, for example, going at the speed of light through time, or if it's travelling at the speed of light through space, it's not travelling through time, and everything in between. So just imagine then a Big Bang. So in a Big Bang, in an explosion, we see things going out in all directions. So if you see an explosion in space, you get things flying out in both directions. In fact, conservation of momentum, the same amount goes one way as it goes the other way. And there's no reason really to assume in a four-dimensional space-time that the same thing wouldn't happen, that equally things would go forward in time as back in time. And so let's just assume that that's the case. So when there was a Big Bang, many billions of years ago, matter was spewed out in all directions, left and right in space, up and down, backwards and forwards, but also backwards and forwards in time. So we're in space here now, and the Big Bang is a long way down there, and we're slowly moving away from it after the Big Bang. Now, everything we see, right, here is going forward in time, right? So matter, we're saying it's going in this time dimension, it's going forward in time, and it's also moving in space. So we're kind of moving out through time and space in a forward direction, right? But what about that antimatter that went backwards in time? So in this model we have, where we have the time dimension, right? Everything that went backwards in time is going to be a long way down there. It's gone out in the other direction in time. This is the time dimension. It's gone the other direction, and so it's so far away in this four-dimensional space-time we can't see it. Just like we can't see things very easily when they're a long way in space, equally with time there's no reason why we'd be able to see and sense the antimatter, because it's so far away in the fourth dimension. So it's a reasonably straightforward matter, right? This position in space and time that we're in, as we've moved out over here, all the antimatter's moved off down there, so we're not in the same place at all. And so why is it that around us then, if we can't see things that are further away from us this time, why is it that everything around us isn't just disappearing, it's in a slightly different position in time? Well, there's a reasonably simple explanation. We all came from the same spot in the Big Bang. So in order to get to this position in space and time, if you're travelling at this constant speed, whichever direction you take, if you're in the same position in space, you're going to be in the same position in time. So everything we see around us is in the same position in the time dimension, and hence we see it quite easily. But the antimatter is literally billions and billions and billions and billions of light years away in time, and we just can't see it. A simple explanation. Is it true? Occam's razor. But let's explore a few other things.